are starting the new topic of synchronous motors. So we'll start with its working principle. So the topics to be covered today are the introduction of the synchronous motor, its working principle, and the effect of load on synchronous motor. Synchronous motor basically runs on only one speed, that is your synchronous speed given by 120 F by P, but it can be made to operate in a large variety of the power factor, that it can operate from the lagging power factor to unity to leading power factor by just the changing of the field excitation. Therefore, the synchronous motor can be made to carry the mechanical load at constant speed, but at the same time improve the power factor of the system. And when it is made to improve the power factor of the system, it is known as the synchronous condenser. So synchronous motors are generally of the salient pole type, but the disadvantage of the synchronous motor is that it is not a self-starting machine. It has to be started by some auxiliary means, and then it will continue to rotate at the synchronous speed. So what are the, basically we try to start the synchronous motor as an induction motor, or a separate starting motor is being used for this purpose, and once the motor starts rotating, it will continue to rotate. The synchronous motors are not much used because they are run at constant speed, but because they possess other unique electrical properties like the having a wide operating range of the power factors, it can be used for different purposes. So how is the working principle, or what's the working principle behind a synchronous motor? Synchronous motor is, suppose for an example, we have taken a two-pole machine. The stator is wound for a two-pole machine. Three-phase winding will be placed, and your rotor is having a also two-pole, and the DC will be applied at the rotor. But when you give a three-phase supply to the synchronous motor, a revolving magnetic field will be produced, same as the induction motor, but it will be setting up a direct current setup at two pole, because the rotor of the synchronous motor is not short circuited, so EMF won't be induced like that. Okay, plus you are going to give the DC supply on the field of the induction synchronous motor. So there will be a situation that the rotor will be having a position, like you can see, NS means the north pole of the stator, SS means the south pole of the stator in the figure, and you have got the rotor poles as north pole of the rotor and the south pole of the rotor. So there will be a situation when there exists a pair of revolving armature poles, that is the stator poles will be revolving while the rotor poles will be stationary. So suppose at any instant this is the situation, then what will happen is, because they are the in the last figure they are the opposite poles, similar poles, so they'll try to repel each other. So the north pole will be coming towards south pole, and this south pole of the stator will be repelling the rotor south pole. But suppose after some time, this is the situation where the north pole is facing the south pole and the south pole of the rotor is facing the north pole of the stator. So it will try to continue to have that position, because that is a stable position. So it will try to continue to remain in that position. But the stator again changes its position, so it's not able to change automatically, and because after every half cycle there is a change of the polarity of the stator poles and the rotor poles are stationary, so it doesn't rotate on its own, and plus due to its high inertia the motor fails to start. Therefore the motor does not have any self-starting torque, and the motor won't be a self-starting motor. So how will we do it? So if the rotor poles is rotated by some external means at such a speed that the interchange of the positions of these poles on the rotor produces a unidirectional torque. So if the stator field is rotating in the clockwise direction, the rotor is also rotated in the clockwise direction, and therefore the rotor poles and the stator pole will have a force of attraction between them, and that is known as the magnetic locking. Once that magnetic locking is obtained, the rotor poles are dragged by the stator revolving field, and it will continue to give a torque in the same direction. So the rotor poles are dragged by the stator revolving field, and hence the rotor rotates at the same speed as the stator revolving field, that is your synchronous speed. Therefore, the synchronous motor working principle only says that it can rotate at only one speed, that is your synchronous speed, and hence the name has been given as synchronous motor. Now when you want to load the synchronous motor, suppose it is under no load condition. So under no load condition, the induced EMF and the applied voltage will be just in opposition, and the stator and rotor will be having the opposite position, and you can see the south pole of the rotor is facing the north pole of the stator, and that will be a comfortable position. So the resultant EMF and the current drawn will be zero, because the motor is said to be on the floating of the lines, because E is equal to V, so no current almost flows. But that is an ideal situation. Practically that is not the case, because practically even the machine is on no load, there will be some amount of no load losses, and therefore a no load current will be flowing in the armature of the synchronous motor, and the E will be falling behind by an angle of del 0 by the voltage. So because of the resultant phasor difference between V and E, there will be a resultant voltage ER which lags behind, and there will be a current which will be lagging behind this voltage ER, given by the angle tan inverse of XS by R, where XS is the synchronous reactance of the armature and R is the resistance of the armature. Because resistance is very small, therefore that angle theta is almost equal to 90 degree. The power drawn on no load will be V I0, that is the no load current, and cos Y0, which is the power factor, no load power factor, and it is just sufficient to meet the losses of the motor under no load condition. Now if you increase the load, when we increase the load, the rotor lags behind the stator field by an angle that is known as the power angle, and this power angle or torque angle increases, and therefore the del increases, and because of the increase in the del, there will be more phasor difference between E and V. So ER will be larger, and if the resultant EMF is larger, naturally the current drawn from the supply side will be more. So the more current is drawn from the supply side over here, but there is not change in the speed. The rotor is still running at the synchronous speed only, but only the angle between the rotor field and the stator field has increased now by an angle del. So when there is an increase in the load, this del increases. So you go on increasing the load angle will go on increasing, but there will be a limit to the increase in the load angle, and that is normally 90 degrees. So if there is too large mechanical load applied to the synchronous motor, the rotor will be pulled out of synchronism, and again it will come to the standstill. So that the maximum value of the torque that a motor can develop without losing its synchronism is known as the pull-out torque. So today we have discussed about the basic synchronous motor. The construction of the synchronous motor is the same as your synchronous generator. Only thing is that synchronous motor size is not the same as the synchronous generators. So we discussed about the synchronous motor working principle and the effect of the loading on the synchronous motor. Thank you.